Hi everyone, welcome back. In this video we'll be demonstrating some of the more common image processing techniques that are often used in computer vision pipelines. And to do this, we're going to build on the camera demonstration from the last video where we sent streaming video from the camera to an output window in the display. However, this time we'll be doing some image processing on the video frames first and then send those results to the output display. So we hope you find this informative, and to get started we'll first take a look at the code and then execute it so we can talk more in depth about the various processing techniques and their associated parameter settings. So starting on line 39, we're defining the 4 different run modes for the script, which include a preview mode, a blurring filter, a corner feature detector, and a canny edge detector. Then on line 44, we're defining a small dictionary of parameter settings for the corner feature detector, and those include the maximum number of corners that the algorithm will return. Quality level is a parameter for characterizing the minimum acceptable quality of image corners. And the way that works is that the corner feature with the highest value in the entire image is multiplied by this parameter, and then that value is used as a minimum threshold for filtering corner features from the final list that's returned by the algorithm. So for example, if you had several features that were detected and the maximum value of those features was 100, then we'd multiply 100 by 0.2, which would be 20, and then 20 would be the threshold for determining whether or not a feature corner was detected. And then the next parameter here, the minimum distance, this is the minimum distance between adjacent feature corners, and this is measured in pixel space. So it's the Euclidean distance in pixel space, which describes how close 2 corner features can be in the list that's returned from the algorithm. And then finally, block size is the size of the pixel neighborhood that is used in the algorithm for computing the feature corners. So this next block of code starting on line 48 is very similar to the code in the previous video, where we're setting the device index for the camera, creating an output window for the streamed results, and then creating a video capture object so that we can process the video stream in the loop below. So here on line 61, we enter a while loop, and first line in that loop is to read a frame from the video stream. And then on line 66, I'm going to flip that frame horizontally, mainly as a convenience for myself so that it's easier for me to point things out in the video stream. And then here on line 68, depending on the run configuration for the script, we'll be executing one of these functions in OpenCV. Of course, if we're in preview mode, we're simply going to take the frame and set that to the result and then display that directly to the output window using IMShow. But for these other run modes, we're going to do some processing first and then send the processed results to the output window. So starting on line 71, here we're calling the canny edge detection function in OpenCV. And the first argument there is the image frame, and then there's 2 additional arguments, a lower threshold and an upper threshold. The upper threshold is used for deciding whether or not a series of pixels should be considered as an edge. So if the intensity gradient of those pixels exceeds the upper threshold, then we'll declare those pixels as constituting a sure edge. And likewise, for pixels whose intensity gradients are below the lower threshold, then those segments will be completely discarded. However, for the pixels whose gradients fall in between these 2 thresholds, we'll consider those as candidate edges if they can be associated with a nearby segment that has already been declared as an edge. So in other words, we're allowing for weaker edges to be connected to stronger ones if the weaker edges are likely to be along the same true edge. And we'll see an example of that when we run the demo for edge detection in just a little bit. Then the next function here is a blur function in OpenCV, and this blur function uses a box filter to blur the image. So the first input to this function is the image frame itself, and then this second input are the dimensions for the box kernel. So this would be a 13 by 13 box kernel that would be convolved with the image to result in a blurred image. So if the size of the kernel is smaller, then the blurring is less, and if the size of the kernel is larger, then you get more substantial blurring. And then finally, for the corner feature detector, converting the frame, the image frame to a grayscale image. And then on line 77, we're going to call the function good features to track. And although it isn't indicated in the name of this function, what this function does is compute corner features. So the first argument is a grayscale image of the video frame, and then the second argument is that dictionary of feature parameters that we described up above. And so what that returns is a list of corners that were detected in the image. And if we have one or more corners detected, then we're going to simply annotate the result with small green circles to indicate the locations of those features. And then after we're done with all this, whatever result we have under whatever run mode we've been working with, we're going to send that to the output stream. So this next block of code here is simply monitoring the keyboard for user input. The script was written so that the run modes could be toggled interactively. So for example, if you were running in preview mode and you wanted to transition to candy detection mode, you would simply type a C on the keyboard. So that's all there is. There really isn't very much code required to implement this. And at this point, we're ready to go ahead and execute the script, and we'll cycle through the different run options and talk a little bit about the results that we see. So this is the preview mode, and here we're simply sending the video stream from the camera to the output window in the display. So what I'd like to do next is toggle through the other filters that we implemented, and we'll start with the blurring filter. So I'm going to type a B on the keyboard, and you can see that the image has been slightly blurred. There's a few reasons you might want to do this. For example, if you had a noisy image, you could apply a small amount of blurring and still obtain an aesthetically pleasing result. But more importantly, in computer vision and image processing, we often use blurring as a pre-processing step to performing feature extraction. And the reason for that is that most feature extraction algorithms use some kind of numerical gradient computation, and performing numerical gradients on raw pixel data can be a rather noisy and not well-behaved process. So smoothing the image prior to performing gradients turns out to be much more robust and well-behaved. And so that's one of the primary reasons we use blurring in computer vision. So now let's take a look at the next option, which is the corner feature detector. So now I've turned that mode on, and you can see a small amount of corner features in the image. There's some here on the microphone. There's a few around my face here, and in particular there's several there in the painting of the horses behind me. And we're going to talk a little bit about how these features are generated based on the input arguments that we selected. And there were two input arguments that we talked about in particular. One was a minimum distance between features, which is fairly straightforward, and the other one was a quality level of the features. So first we'll talk about the minimum distance. So here I've got a textbook with some very well-defined characters on the front that have nice sharp edges, and we're detecting all kinds of corners in those characters. You can see that each of those letters probably has 2, maybe 3 corner features for each character. But when I move the book much closer to the camera, you'll see now that there are several more corner features associated with each character, and the reason for that is that those letters are much larger in pixel space. So now I'm not constrained by the minimum distance between the features because I've made the letters so much larger in pixel space. And then one other thing I'd like to talk about is drawing your attention to this section of the book here with this graphic image on it. If I put this very close to the camera, we're going to see that we detect all kinds of corners associated with the dots in that pattern of the book there. So the reason those are jumping around so much is that I'm having a hard time holding the book really still. But the main point is that I'm getting all these detections here. Now watch what happens when I lower the book and expose the text from the title of the book. As soon as I expose the text from the title, all the features associated with the graphic image below have been filtered out. So let's take a look at that again. I raise the book and I get all these features here. And now when I lower the book and expose the title of the book, all those have been filtered out. And the reason for that is that that quality level threshold we talked about is based on the highest score for a corner feature in the entire image. And because the corner features associated with these characters in the title of the book are so much stronger, their feature score is higher, and therefore we're effectively raising the detection threshold for corner features. So I just thought that was an interesting example of how that parameter is actually used and how it can affect the algorithm in your particular application. So finally, let's go ahead and cycle to the canny edge detection. So toggle to that mode, and so now you can see the results of edge detection here. You can see the microphone is very well defined. The corner of my shoulder against the light background of the wall is very well defined. And then up here behind my shoulder, you see a painting of some horses, and the subject matter in that painting is partially defined, but there's a lot of broken edges in that painting. And so I thought it'd be interesting to talk about the threshold inputs for the canny edge detector and see if we can improve what that looks like. So before we do that, I'm going to make a screen snap of this video feed just so we can have something to compare to. So I'll put this aside, and now I'm going to edit the threshold for the canny edge detector. So previously the lower threshold was very close to the upper threshold, so there wasn't much opportunity for us to find some weaker edges and connect them to stronger edges. But if I lower this to something like 80, we now have an opportunity to consider weaker edges that might be associated with the stronger edges. So I'm going to go ahead and run this, and now we'll put these side by side for a comparison. So if you take a look at the image down below, you can see that again the outline of the horses was rather broken in some places, and now if you compare that to the video stream up above, you can see that there's been some improvement. We're effectively extending the definition of these edges because we're allowing those edges to be connected to weaker edges that were in between those two thresholds rather than discarding those edges altogether. So I thought that was an interesting way to demonstrate how those inputs affect the results. Obviously, all these algorithms require some experimenting and tuning, and things that will depend on your particular application. But we hope this was a nice introduction for you, and definitely encourage you to take a look at the OpenCV documentation on these functions and other functions, and write similar scripts like this one here and do some experimentation. So that's all we wanted to cover in this video, and we'll see you next time. Thank you.